Let's say we have a graph of function f, and let me draw the x-axis. So it is about perpendicular to the y-axis, and I'm having very hard time doing that. Okay, that looks reasonable. And let's say we have our function f going like this, and you want to find the area under the function f from x equals to a to x equals to b. So this area is what you want to find. So you want to find area under the graph of f from x equals to a to x equals to b. And how we write this mathematically is like this: integral from a to b of f of x dx. All this means for non-negative function, we are going to extend this definition to the functions that can be negative later on. But for now, all this is the area under the graph of f from x equals to a to x equals to b, and this is definite integral. We call this definite integral of f from a to b. So this is all the definite integral is. But now you may ask, how can we define definite integral mathematically? Again, if you remember from a video from long time ago, the definition for derivative f prime of x was limit as the delta x, or width of interval, is getting closer and closer to 0 of f of x plus delta x minus f of x over delta x. This is very important, and you need to know this relation for the AP test. And if you're confused, if you forgot this, you may see I with a circle popping up at around here-ish, and if you click it, it will take you to a link to video that's about proving or showing you that f prime of x is limited this limit, and telling you intuitively why f prime of x is defined like this. But that's not the point of this video. This video is definite integral, and we want to write down definite integral from a to b of f of x dx in using limit in the similar way as f prime of x. And the reason we want to write this limit, because it makes it formal. Because limits are formal using epsilon delta definition. I never made video on that, but in the future I think I will. Because epsilon and delta makes limits formal, defining f prime of x and definite integral of f using limits makes them mathematically formal too. So it's not something out of thin air, but something concrete mathematically. So how can we define this? Once again, how we're going to do it, and you may remember the Riemann sum, where we divided the graph of f, we use y equals to x squared into various rectangle, and we added up the areas of the rectangle to approximate the actual area under the curve. And we are going to do a similar thing. Let's say that's half, and you're going from a to b. Let's say we are using n sub intervals, or you can also think of it as being n rectangles. So we can draw, let's say n is 2. So in this case, we can draw one rectangle like this. We can draw one rectangle like this. Actually, let me actually go more in depth. Let's start by dividing x into two pieces. So that's our first interval, and that's our second interval. And then we're going to pick a point in each interval. Let's say we pick this point, and let's call this c sub 1. And for this one, we pick this point and call this c sub 2. What we are going to do, we are going to go up to the function, and where it hits the function, so the height is f of c sub 1, and for this one, height is f of c sub 2, we are going to draw a rectangle with the width of the interval and the height of f of c sub 1 and f of c sub 2. So that's going to be the first rectangle, that's going to be the second rectangle. So what's the areas of the rectangle? The first one is f of c sub 1, which is the height, times, let's call it delta x. Height of the next one is f of c sub 2 times delta x. So we can think of we can think of the sum of the areas of the rectangle, which is an approximation of the actual area under the curve, as we're summing up. Remember, sigma definition is used to sum up the various pieces, and if you forgot how to use it, you may see another eye popping up. You can click it and it's going to take you to a video where I introduce you to the sigma notation. Okay, let's get back to it. We want to sum up all the areas of a rectangle from the first rectangle to the nth rectangle. In this case, n is 2, but we may have 3 rectangles, 4 rectangles, 5, 6, and so on. And we want to multiply f of c sub I. So some c sub I inside its interval, and evaluating the function gets you the height, and multiplying it by delta x, which is the width, gets you the area of the rectangle, and you are summing up the areas of the rectangle. So this is the Riemann sum. This is the Riemann sum. Once again, the sum from I equals to 1 to n of f of c sub I times delta x is the Riemann sum. But what do we do? What do you want to do with the Riemann sum? Well, let's think about it. If we use 2 rectangles, our approximation is going to look like this. If we use 4 rectangle, so n is 4 from A to B, our approximation is going to look 1, 2, 3, 4, something like this. If we use 8 rectangle, our approximation is going to A to B, going to 1, 2, 3, 4, 5, 6. That makes 1, 2, 3, 4, 5, 6, 7. Let's draw one more. Our approximation is going to look something like this. And let me ask you the question. Let me erase these parts of the rectangle that we do not need. Which one gets you the closest estimate of the area? And you're going to say n equals to 8, because the more rectangles you use, the closer they are going to, in general, represent the area under the curve. So we want n to approach infinity. You want to use as many rectangles as possible. If we use technically infinite amount of rectangles, summing up the areas of the rectangle is going to get you the exact area under the curve. So we're going to take limit as n approaches infinity, and that's the definition of definite integral. Let me rewrite that. Integral from a to b of f of x dx is limit, as we have infinite amount of rectangles, of sum from the first rectangle to the nth one, of sum our function evaluated as some function in the interval times the width. And this is the definition of definite integral. And you may ask, why do we write it like this? This is the area under the curve. This is the area under the curve. And we know if we do not have this a and b, we have indefinite integral, which is anti-differentiation. This thing is the opposite or inverse of differentiation. And you may say, finding area under the curve and doing opposite of differentiation, they don't seem like the same thing. How are they related, and why are we using the same sign for definite integration and indefinite integration? Are they related somehow? And you are going to be correct. They are related somehow, and it is by fundamental theorem of calculus, arguably the most important theorem in all of calculus, because it connects differentiation and integration calculus. And I'm going to make another video on this in the future.